Let's see another example of power series. Let sigma of -1 to the power of k, x to the k over 12 to the power of k, as k runs from 0 to infinity, be a power series. Part 1, find the interval of convergence. Okay, so similar to the examples that we saw in the previous video, let's use the root test. If the limit as k tends to infinity of the kth root of absolute value of the general term, which is -1 to the power of k, x to the k over 12 to the power of k. If this is less than 1, for sure for these x's, the series is convergent. Let's see how we deal with this inequality. First of all, it's an absolute value, so that -1 to the power of k disappears because -1 to the power of k for even case is 1, for odd case is -1, but when we apply the absolute value, that disappears. So what we have is kth root of x to the power of k. When applying absolute value to that, becomes absolute value of x to the power of k. 12 is already positive, so it doesn't need absolute value. Kth root of this fraction. This fraction, both the top and the bottom, has the power of k, so we can simplify that. So the k, and in this case, they cancel out. In other words, what we have is the limit as k tends to infinity of absolute value of x over 12 is less than 1. Since there is no k remaining, we don't need this absolute value. I'm sorry, we don't need this limit sign as k tends to infinity. We only have the variable x. So absolute value of x divided by 12 is less than 1. If we multiply 12 by both sides, absolute value of x is less than 12, meaning that the interval of convergence is from -12 to +12. So this is the interval of convergence. So the interval of convergence is from -12 to +12. Let me write convergence, the entire word, interval of convergence. Obviously, the second part is quite simple because find the radius of convergence. So here the interval from -12 to +12 on the real line. The center, so in fact, this is the interval from -12, the open interval, and This is 0 in the middle. So the radius of convergence, which means the distance from the center of the interval to the endpoints, that r is 12. So the radius of convergence is 12. By the way, this interval of convergence in this example is an open interval because if you let x be 12 or minus 12, you will get a divergent series. In this regard, I also need to mention the Taylor series of a function. So over here, we have a function f of x, and suppose it has derivative of every order. So we have f prime, f double prime, the third derivative of f, the fourth derivative of f, and so on and so forth. So suppose f has all the derivatives, of all the orders. We can define a series, which is called the Taylor series, related to f or associated to f. First, let a be a number, a constant number. We can define the Taylor series of f as follows, that it is the Taylor series of f of x at a is f of a plus f prime of a over 1 factorial times x minus a plus f double prime of a over 2 factorial times x minus a squared plus, let me continue down here, f triple prime, or the third derivative of f at a over 3 factorial times x minus a to the power of 3. And we can continue so on and so forth. So we get a series, which is called Taylor series of f of x at a. For simplicity, sometimes we let a be 0. If that a equals 0, the Taylor series we can still call it Taylor series when a is 0, but there is another name for that. The Taylor series is called the Maclaurin series. So again, the Maclaurin series of f of x is f of 0 plus f prime at 0 over 1 factorial times x plus f double prime at 0 over 2 factorial times x squared plus the third derivative of f at 0 over 3 factorial times x cubed, and we continue this with other powers of x. This is called the Maclaurin series of f of x. One important thing about this is for some functions, they are equal to the Taylor series, or if we are considering the Taylor series for a equals 0, the function is equal to its Maclaurin series. For example, f of x equals e to the x is equal to its Maclaurin series. So let's write down the Maclaurin series of e to the power of x. We know that if f of x is e to the x, the first derivative is e to the x. You know that for the exponential function e to the x, the first derivative e to the x. The second derivative is also e to the x. Or in general, the nth derivative of e to the x is still e to the x. So at 0, f of 0 is e to the 0, 1. F prime at 0 is e to the 0, 1. F double prime at 0 is e to the 0, 1. And the nth derivative of e to the x at 0, still it is what? So let's see this Maclaurin series for e to the x, uh, how it looks like. Maclaurin series is f of 0, which is 1. F prime at 0 is 1 over 1 factorial times x, so it becomes x. The third term is f double prime at 0 over 2 factorial times x squared, so 1 over 2 factorial times x squared. The next term, 1 over 3 factorial x cubed, and so on and so forth. So in fact, as I mentioned, e to the x is equal to its Maclaurin series. So e to the x is equal to this series, or if I want to write it in the sigma 4, as you can probably guess how we write this down. It is x to the power of n, or let me go with k. It's okay, we can use n. X to the power of k over k factorial as k runs from 0 to infinity. So the first term is when k is 0, and remember that 0 factorial is 1. So when k is 0, x to the power of 0 is 1 over 0 factorial gives me the first term 1. When k is 1, I get this term. When k is 2, I get this term, and so on and so forth. So as I mentioned, for some functions like e to the x, like sine x, like cosine x, the function is equal to its Maclaurin series. Another example that the function is equal to its Maclaurin series, as I mentioned, is sine x. So f of x equals sine x is equal to its Maclaurin series. So as a practice to write the Maclaurin series of sine of x. So the Maclaurin series of f of x equals sine x. Remember that when we have f of x equals sine x, the derivative of f of x is, let me start from further left, so I'll have enough room for more terms to include. So if f of x is sine x, f prime of x is cosine x, f double prime of x is negative sine x. The third derivative f triple prime of x at x is minus cosine x. But the fourth derivative, I come back to sine x. The fourth derivative is again sine x. So the fifth derivative is cosine x. The sixth derivative is minus sine x. So these four will be repeated, as you have seen in Calc 1. So let's see what happens at 0. F of 0, sine of 0 is 0. F prime at 0, cosine of 0 is 1. F double prime at 0 minus sine of 0 is 0. The third derivative of f or f triple prime of sine, or the third derivative of sine is going to be minus cosine. So at 0 is minus cosine of 0. So f triple prime at 0 is negative 1. After this, these numbers 0, 1, 0, minus 1 are repeated. So the fourth derivative of sine at 0 is 0. And so on and so forth. So if I want to write the Maclaurin series of sine, which gives me the sine itself, f of 0 is 0, and then I'm just using the formula for Maclaurin series. F prime at 0, which is 1 over 1 factorial times x, so it is x. The next term is f double prime at 0, which makes the whole term 0. The next term is going to be f triple prime at 0 is minus 1 over 3 factorial times x cubed. If you continue this here, I just found the first fourth derivatives. The next one, again, 0. The next one is going to be 1 over 5 factorial x to the 5. Then I will have a 0. The next one, minus 1 over 7 factorial x to the 7. And so on and so forth. So for the sine, all the even powers of x disappear because the coefficients are 0. So sine of x will be equal to x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial, and so on and so forth. If I want to write this in the sigma form, sine of x will look like something like this. The first term is positive, and so it's an alternating series. Sine of x is an alternating series. The best way to do this, as we have seen with other alternating series before, here I can put minus 1 to the power of k, and k runs from 0 to infinity. But I cannot just put x to the k because some I see only odd exponents are there. So it is x to the power of 2k plus 1. This only gives us only the odd powers over 2k plus 1 factorial. So in fact, sine of x is equal to this Maclaurin series of sine of x.